Pero tú me avisas, ¿no? Cuando empezamos. Ah. Hello. Está abierto. Hello. Welcome to the session poster. Session P3. Now we start with the poster Micromorph and Polyform Solar Panel in Warm Temperature Transitional Climate Comparison of Outdoor Performance and Simulation from the University of Science and Technology of Poland.
Good afternoon, everyone.
Good afternoon.
My name is Katarzyna Dynda, and I'm from the University of Science and Technology in Kraków in Poland. I would like to present a poster about my paper, Micromorph and Polymorph Solar Module in a Warm Temperature Transitional Climate Comparison of Outdoor Performance and Simulation. The measurements were taken in the Education and Research Center for Renewable Energy Sources and Energy Conversion at the AGA University of Science and Technology in Kraków. I will present results for two modules, Micromorph and Polymorph modules, that electrical parameters for standard tested conditions are compared in Table 1. The measurements were taken during the 4 seasons, autumn, winter, spring, and summer. During the study, I measured the air temperature and humidity, and the results I show in the figure 1. Also, I measure the power generated by both modules, and measurement results are shown in figure here. Based on the results, it can be concluded that spring and summer spectra are close to the standard daily power output. Large power change are observed during the winter and autumn. From the obtained results, it can be concluded that the changes in the input power are not correlated with either temperature and humidity, but the output power is strongly influenced by changing climate. Definitely higher power value are obtained in the summer day analysis. The power output signal on both cells is similar for both cells. In this work, I have also made a simulation of an installation that consists of both types of modules. To the simulation, I use the Polymer program. The maximum power obtained with the two recording methods is strongly varied. This clearly observed the winter. Maximum value higher than expect for the recorded outdoor performance values appear, which may be due to additional factors such as temporary cooling due to the atmospheric factors. For the micromorphic cells, the outdoor value turned out to be more favorable than the value obtained in the simulation with the Polymer program. The increase in maximum power it was twice as higher in winter and spring, while in autumn the actual value were 50% higher. But in summer, simulation and measurements show the same value. In the case of the polymorphic panel, also the maximum powers are higher for outdoor performance. In the case, the significant change is only in the spring season. Both panels perform better than expected, confirming that photovoltaic is a promising and efficient renewable energy source for the future. The results also point the need for intensified outdoor research and as well as the importance of obtaining better and better simulation models. Thank you.
Thank you, Mrs. Dindal. Now we start with the next. Hello? Now we start with the next poster. Less charging to the system. Let's try. Are you ready?
Can you hear me? I'm ready.
If you're ready, you can start, please.
Can you all see the poster? Okay, so I'll present my work, which is entitled The Behavior of a Low Voltage Distribution Network with Crescent Photovoltaic Generation Penetration and Presence of Energy Storage Elements. My name is Rafael, I'm from University of São Paulo here in Brazil, and I'll start the presentation. This work is the proposal of studying the increasing interest of distributed photovoltaic generation in Brazilian households. This presence of this type of resources in the low voltage grid can cause the reverse power flow in the network, causing problems like overvoltage and voltage imbalance. So we have suggested utilizing the storage system to prevent this reverse power flow in the grid, smoothing the consumption profiles, storing the surplus generated energy on the storage system, and using it at a more opportune time. This work has 3 simulation phases to analyze this proposal. The first is to the original test grid to see how it, after we increase the distributed photovoltaic generators to observe its effect on the grid. At last, integrate the energy storage system in 2 configurations. First, as individual systems connecting the storage with the generators at the consumption point, and later we connect a bigger storage system which will work for all the network. So the first figure we see the distribution grid test that we will use. There is 34 consumers and 41 buses. The medium voltage side, it has 11.4 kilovolts, and the secondary low side is 220. So in this first figure, we see the profiles of the different level of penetration. With higher penetration, we have higher reverse power flow. This heat maps represent the voltage in all buses. At a normal condition, it works at a nominal voltage with a voltage drops in the higher point of power demand. With the increase of maximum PV penetration, we have over voltage during the day. Now integrating the individuals, we have this prevent the reverse power flow and improve the voltage profiles during all the day. Here with the energy storage, we have the same effect, but with the unbalanced power on the three-phase of the transformer, we have a higher unbalance on this situation. So the conclusion is that with the increased penetration of photovoltaics, we have this problem. We can improve them with the energy storage, but in the condition of the concentrated energy storage, we have a higher imbalance, which could be a problem. I'm sorry for the confusion. I'm not prepared, but I finished here.
Many thanks, Rafael, for your presentation. Now, if we have no more online presentation, we will continue with the recorded one, the poster 282, software for calculating the optimum tilt angle of PV modules in different latitudes of southern hemisphere and solar plant sizing, by the University Federal Institute of Education, Science and Technology of Goiás from Brazil.
Hi everyone, I'm Professor Marcelo Escobar de Oliveira from the Federal Institute of Goiás, campus Itumbiara, from Brazil, and Goiás in the middle of Brazil here. And I'm part of the research group of energy systems called RUPSI, okay? And first of all, it's a pleasure to be here participating of another conference. And I'm here to present our work called software for calculating the optimum tilt angle of PV models in different latitudes of the software hemisphere and solar plant size. Well, this work started with a need to develop a software that was used for the electricity market, especially in Brazil. Yes, this work was developed for 3 students, graduate students of electrical engineering here in a subject called Applied Computer Systems. And well, the software is a simple software. This is the first version of the software. Here's a screen of this tool. So the input variables, it's so simple. We need the installation location and the surface, as the localization, the latitude, and you have the information of this as a result of this this software, you have the best installation angle for a given latitude, the number of models from the size of the location site, the maximum power generated from internal calculations. Well, to calculate the best installation angle, you use the method of Liu and Jordan, yes, which describe the radiations that reach a flat surface installed in the Earth, and also the optimization uses the particle swarm optimization, yes, to reduce the calculation time to maximizing the radiation that arrives from the models by varying the installation angle, okay, between 0 and 19 degrees. Well, the amount of models is calculated considering the shading effect like this figure, okay. And well, about the result, we can talk about this, that the software has a good speech for particle swarm optimization. The optimal angles for all Brazilian capitals were obtained, like we can see in this table here, the angle, okay, and the solar radiation here, and here in the latitude. Well, in this result, we can see that the cities that are closer to the equator line have an angle of 0, like here, Macapá. It's closer to the line, the equator line, okay. And the cities that's more in the south or in the south, and the angle it's bigger than the Amapá, for example, okay. Well, so we conclude that this is a software with efficiency, usability due to particle swarm optimization, and also returns important outputs to the user, considering little input data, okay. So you can see here in this screen. Well, and it's a simple software. It's the first version, and you want to continue this work to improve some variables in this software, okay. Well, I want to thank the entire organization, and Professor Manuel and his team, and always he's give us a support, and I'm very sad to not to be present on the conference, but we know that it will be a success. Okay, thank you very much. Bye. Hello everyone, I'm Professor Marcelo Escobar Oliveira from Federal Institute of Goiás, campus Itumbiara, and I'm part of a research group of energy systems called NUPSI. We are from Brazil, and I'm here to present our paper. And first of all, it's a pleasure to be here, participate of another ICRAPID, and I'm here to present a paper developed for a student, a graduate student of electrical engineering in our campus. And the paper is impacts of photovoltaic systems on a Brazilian distribution feeder using OpenDSS. Well, this paper is a simple simulator. Consider we have different scenarios to analyze. Yes, consider the impact of the photovoltaic in a specific feeder here in Brazil. This figure presents the feeder. Yes, it's large, and the first scenario we put 1.15 megawatt equal of photovoltaic, and the scenario 2 you put more 2.45 meg. So here you use these shapes of these curves of the load curves of a residential in green, industrial in blue, and a commercial curve in yellow. We consider different kinds of consumers on the feeder. Here in Brazil, we have a difficult to obtain this kind of curve. Yes, this specific. So use these typical curves of each one consumer. Okay. So here you have information about the feeder. The nominal voltage here in Brazil so common 13 kV, and transformers, total power transformers, feeder stations, large feeder, yes. Number of residential consumer, number of commercial consumers. We can see here is this typical residential feeder, yes. Number of industrial consumers is on 2 here in this case. Well, we use the OpenDSS approach, yes, and here we can see some results of the simulation. Here the total active power, and the first scenario is the yellow, sorry, the second scenario is in green here, and here we have the demand active power in blue. This figure shows the losses of the system during the day, during a typical day, yes. And you can see here when you simulated without the EGT generation, yes, without photovoltaic systems, we have the red case, and the first scenario black, when we have the little units of the PV systems, and after when you increase the PV system, you can see here in blue the increase of losses of the systems. Yes, this file, these figures we can see the voltage levels here without PV systems. Yes, you can see a decrease of the voltage. Here, when we put some PV system, we can see the improve of the voltage level. And here, consider of course in the substation 1 PE, you can see the voltage level increase a lot. Yes, when we have a lot of PV systems in this feeder. Okay, so it's concluded that is near future in the insertion of PV will cause serious consequences in the future, how you can see here, yes. So it's a simple analysis, but this we can see in a real Brazilian distribution figure, yes, what is working. The analyses are very important to the utilities, of course, and the regulators to define actions that they touch the considerable increase of PV in distribution system. Well, that's all. I'd like to thank the organization, mainly Professor Manuel and his team. Always he's giving us a support, and I'm sad to not be presenting the conference this year, but we know that it will be a success. Thank you very much. Bye bye. Hi everyone, I'm Professor Marcelo. Hi everyone, I'm Professor Marcelo Escobar de Oliveira from Federal Institute of Goiás, campus Itumbiara. I'm part of a research group of energy system called NUPSI, and we are from Brazil. Well, first of all, it's a pleasure to be participating in another conference, and well, I'm here to present this work called Loss Analysis due to influence of harmonics in a distribution system. This work was developed by for a student of electrical engineering from our campus. Well, the work presents an analysis of electrical losses in distribution systems, considering nonlinear loads and consequently harmonics. Consider three cases: cold, mild, and hot days. Okay. For the analysis, a modified IEEE system was used because to use a Brazilian system was very difficult to find a good system to analyze this, and use this system, and we adapted it using some parent from Brazil. Okay. Well, and this system is available in Open DSS. Okay, so the system was adjusted so that some parameters, such as voltage levels, like I said, were closer to the Brazilian electrical system. The system, the load curves are obtained using fuzzy logic for different climate cases based on occupation. Yes. So rules were defined through the days in such a way depending on the occupation, residential or commercial load, okay, consumers. From these rules, the curves were obtained, like you can see in the figure 1 here. Yes, and this figure shows the load curves for hot, cold, and mild days. As mild and hot days in Brazil are very similar, okay, especially in some states in Brazil. Only one curve was generated for these two commercial cases, where the use of, for example, air conditioning is present of these two types of days. In relation to residential curves, we have three different curves in the analysis: cold day, mild day, and hot days. Okay. For this analysis, it was it's also necessary to collect data of harmonic spectrum for the different loads, how we can see here in the table 2. Okay? And that may be present in Brazilian distribution system. Well, and this table presents the magnitude, the angle, certain of each equipment. Okay, this is maybe the most difficult part of the data to obtain. Yes, well, and the system used has loads. So according to the table 2, we can see here the quantity of loads. You have almost 600 loads of the system, and you divide it in some spectrum, harmonic spectrum, and the load shape. Okay, well, a total of you have a total of 7 kVA of photovoltaic system was inserted. And what else? With the system ready, and the study of losses to the harmonics was currently out in OpenDSS using the software because it's very good to analyze these cases, and user interface with MATLAB. Okay, to calculate the power flow for each climate, okay, in each case, and here we can see the results. Here we have the loss to the harmonics of order 3 to 9, yes, and here we have to the harmonics of order 11 to 19. Okay, for each case the flux was considered every hour, okay, performing the fundamental power flow, and then for each harmonics. Thus the results you can see here. For each case 1 is cold day, case 2 it's a mild day, and case 3 it's a hot day. Okay. For more, these losses for all harmonics are greater for hot days, how we can see. In figure 4, and it's clear to observe the influence of losses to the harmonics in the system. Yes, and you have heard, for example, this 20% being basically divided between the third, 50, 70, and 90 quarter harmonics, while the other harmonics cannot reach 1% of losses. Okay? How we can see here. Therefore, it's appear that there is a considerable influence of harmonic in the calculation of electrical losses in distribution networks. However, the difficulty in having information about these harmonics is the networks it's known. Okay. Well, that's all, and I want to thank the entire organization of this conference, especially Professor Manuel and his team, who has always given us support, and very sad to be not to be present at the conference, but we know that it will be a success. Thanks a lot. Bye bye.
Okay, hello. Now we go on with the next one. 314, fuses in distribution system, new applications in DC circuits, from Rio Cuarto National University, from Argentina.
Fuses in distribution systems, new application in DC circuits, authored together with my colleagues, Professor Thorn, Ranieri, and Romero. The vast majority of distribution systems currently use operate in electrical distribution with alternating current in 50 Hz or 60 Hz. Today, technological advances are reviving research on DC type of fuses, mainly due to the trend toward the use of distributed renewable energy, which handle electrical energy in the form of direct current. Also, there are continuous end-use applications, such as centralized variable speed drives and the rapidly growing application in electric cars, which has recently started. The main field of application of the direct current fuses arises from the massive application of three types of equipment: photovoltaic generators, among other generator types, the electrical car, and large storage batteries. In direct current circuits, once the circuit is closed, the current grows to its final value determined only by the resistance of the circuit, based on an exponential curve whose growth rate is fixed by the circuit time constant, usually measured in milliseconds. The magnitude of the fault current in relation to the load current have very different values, with extremes of 20 times in the case of circuits powered by batteries to 1.15 times when the source is a photovoltaic cell, passing for 12 if powered by a rotary generator. The operation of a fuse in a DC system has three fundamental parts: pre-arc, arc, and post-arc processes. Pre-arc process: the heating and melting processes, if the current is sufficient to reach the melting temperature of the fuse element, are analogous in alternating current and in direct current. Arc process: the operation of the fuse, pre-arc and arc, is simpler and safer when the current values are high and grow rapidly, that is, short circuit, which in the case of direct current must also have a low time constant. Post-arc process: the post-arc fuse operation requires of much more analytical and experimental research. The protection of general equipment, which fuses, is achieved through the concept of providing, through the protective device, a barrier that interrupts the current before it can damage the protected equipment, or shorten its useful life too much. The main modern applications are on battery circuits, electrical vehicle circuits, power electronics, solar panel circuits, mass public transport, mining. It is concluded in the need of deepen the study of this application in order to achieve specific fuse designs for direct current. It is necessary to extend the knowledge of the behavior of the fuse against variable and repetitive loads. The DC arcing process must be improved through the development of more accurate models and the performance of extensive experimental validation aimed at ensure the extinction of low-volt current. It is necessary to understand the effect of the presence of transients that were not normally in alternating current use. Many thanks for your attention.
We will continue with the next oral poster presentation with the title Protection of Power Semiconductors in Inverters Using Fuses and Their Coordination with the Protection Scheme of the Distribution System, from the Technological National University from Argentina.
Fuses and their coordination with the protection. Good afternoon, ladies and gentlemen. My name is Juan Carlos Gómez. I am from the Department of Electricity, CITAI, National University, Argentina. I will present the poster corresponding to the paper titled Protection of Power Semiconductors in Inverters Using Fuses and Their Coordination with the Protection Schemes of the Distribution System, authored together with my colleagues Professor Baschetti, Fiumetto, Arcurio, and Coyos. The integration of distributed energy resources implies an important challenge for the protection of the distribution network due to the incorporation of devices with less capacity to withstand normal disturbances, particularly in front of overcurrent and overvoltage. The increasingly widespread use of power electronics incorporated in rectifiers and inverters, which due to its weakness require high-speed protection devices, complicate coordination with the traditional protection of distribution systems. Today, semiconductors have the characteristic of being capable of conducting high load current values. Moreover, they are very weak to overcurrent and overvoltages. The information of this semiconductor capacity or ability is one of the parameters that must be inevitably be controlled by the fuse. In general, fuses in distribution system have a very high breaking capacity, but they have limitations in the interruption of the slight overload. Thus, the AR and GR classes appear, in contrast to those traditionally used in distribution system. The response characteristic of these ultra-fast fuses oblige the professional in charge of the protection of the distribution system to have a deep knowledge about the behavior of the power electronics in the face of overcurrent, and to know how the fuses, through the selection of its rated values and characteristic curves, it. Due to the complexity of this coordination, the fuses must have more complete operation information. The protected coordination task is based on confirming that the stress allowed to pass through the protected fuse does not exceed the energy supported without damage by the protected device, and also that the overvoltages generated in the limit operation case do not damage the device connected in parallel with the protected one. In other words, the coordination work is a simple comparison of the parameters of both devices. The coordination between protected devices against overcurrent is based on the comparison of the characteristic time current curves, which here is applicable only in the validity zone of the homologous curve of the semiconductor. For high fault currents, the ultra-fast fuse will always operate before the distribution system device, although if they are needed, they can be coordinated based on the I2T values affected by the corresponding correction factors. It is concluded that in-depth Knowledge of the dissimilar characteristics of power electronic devices and the usual devices of the distribution network with regard to their protection are essential to obtain maximum use of the traditional scheme, with the addition of distributed renewable sources. Many thanks for your attention.
We finish the poster session and we are in time for continuing with oral session A4 with the next oral presentation 312 dual axis tracking electrical drives for solar power tower from the Department of Electrical Engineering of King Fahd University for Petroleum and Minerals from King Saud, Arabia, and the Georgia Institute of Technology, USA. If you are ready, you can start, please.
Hello.
Hello, you can start, please.
So you can see my screen now? Hello?
Hello, go on, please.
Yeah, okay. Yeah, okay. So hello everyone. I'm Abu Bakr Salim, Assistant Professor at King Fahd University for Petroleum and Minerals. Today I'm going to represent our work in the title of Dual Axis Tracking Electrical Drives for Solar Power Tower. The authors are Walid Hamana, Abu Bakr Salim, Muhammad Abidu, Thomas Habitler, and Abdulaziz Toiban. The topics of our presentation: firstly, there is an introduction to concentrated solar power and solar power tower topology, then the study objectives and the proposed work. Then we will go in deep a bit in solar power tower and modeling and analysis of dual axis tracking systems. After that, we will discuss the electrical drive systems used in solar power tower. And finally, we will discuss the experimental results of our prototype and our results. This work is made under a project called Advanced Heliostat Drive System for Concentrated Solar Power Tower. This project is a collaboration between two teamworks, one teamwork in KFUPM at Saudi Arabia with the Professor Abidu, Abu Bakr Salim, and Walid Hamana, and in the side of Georgia Tech team in United States, Professor Thomas Habitler and Abdulaziz Toiban. Firstly, our motivations to invest in solar energy. As we can see here in the right-hand side, we can see the irradiation of solar and the amount of incident solar energy in the region of Saudi Arabia. This amount is very huge and it's promising. So, as also the vision of Saudi Arabia 2030, we are going to generate 50% of our demand from renewable energy. So it's very important to take care about thermal or solar energy in Saudi Arabia. So it's a great opportunity to invest in this. Sorry, any question?
Nothing, Dr. Abu Bakr. No, sorry. With you, Walid.
Okay. So, concentrated solar power. What is the concentrated solar power in general? Concentrated solar power means we need to concentrate the solar irradiance to a certain place in order to collect the energy coming from the heat. So this is the meaning of concentrated solar power. The largest advantage of CSP system are providing dispatchable power as well as the huge heat storage capacity. This is very important in CSP systems. Also, storing thermal heat is much easier and cheaper compared to electrical system. We know storage system in electricity have a lot of issues compared to thermal storage. So it's very good to find another way instead of the small lifetime batteries. Additionally, CSP plant is quite friendly to power grid and offering high quality electricity even during night. This is because of the thermal storage. However, one main issue with CSP in general is the cost of CSP, because the cost of CSP is still high a bit compared to different renewable energies. In terms of cost, here we have just a chart comparing the difference between prices of kilowatt hour between wind energy as offshore and onshore, and also PV with CSP. As we can see recently, at 2020 and 2021, the prices of CSP became smaller compared to previous. This is due to the spreading the technology in the world. And by the way, it's expected also to be reduced more and more by 2050. In one of the studies made in Germany, they said that the cost of PV and CSP will be equal at 2050, expected to be equal. So it's very promising technology. So this is why we are motivated to make research and work in these technologies. We can classify CSP technologies into two main categories based on the way of concentration. First way is the point concentration, and the second way is the line concentration. So we can concentrate solar power into a certain line. Two technologies are used to concentrate in points, like solar power tower, and this is what we are going to discuss in detail today, and all parabolic dash. Another two technologies are parabolic trough and linear Fresnel. These two technologies are used for line concentration. Here, this is a well-known figure for simplified figure for the different four technologies. This is called solar power tower technology. It's just some mirrors, and these mirrors are reflecting the moved sunbeams all of time to a certain point on a solar tower. For that, we call it solar power tower. And heliostat, if the word means mirror, each unit, all of these units are called heliostats. Another technology, which is the parabolic dash, it's also point concentrator. As we can see, this dash will move according to the sunbeam direction in order to reflect these sunbeams onto a certain point. So this is the second technology, which is point concentrator. The other two technologies are line concentrators, like as we discussed here. This is called the parabolic trough. The trough itself, the parabolic trough, is moved in order to collect the reflected sunbeams on tubes here, and inside this tube there will be a fluid that can be used to store energy after that. And this is another technology which is called linear Fresnel. It's based on linear mirror instead of parabolic one, and it's reflecting also sunbeams onto a collector in the center. So these are the most well-known topologies for CSP. Now, if we would like to make a comparison between the four technologies, we can see that according to the collector type, these are the four types we discussed. For the collectors, for linear Fresnel, we have flat mirror. For parabolic trough, we have parabolic cylinder. For solar power tower, which is our target, it has mirrors, linear mirrors called heliostat. And for parabolic dish, it's used parabolic mirror. The heat transfer can be made using different fluids, as we can see here: water, thermal oil, water or melting salt or air, and so on. If we compare the efficiencies of the four types, we can find that the highest efficiency can be obtained from solar power tower. This is for sure because of the high temperature. As we can see, if we compare temperatures also, we can find that the highest temperature levels can be achieved using this solar power tower. So this is our motivations to work in this type of technology. So by the comparison, we could recognize that the overall efficiency and temperature is high in case of solar power tower. Also, the efficiency of central receiver solar thermal power plant depends on the ability of heliostat to reflect the sunbeams. Because if we don't have accurate reflecting from these mirrors, we cannot collect this heat. So we need a very accurate system, very accurate drive system in order to reflect the sunbeams all of the time. And this is our target as an electrical engineer. Also, reflecting the sunbeams over the course of a year requires an accurate drive system to move the heliostat over a wide range of azimuths and the elevation angle. This is very important to have wide range of azimuths and the elevation angle to collect the sunbeams during the year in order to get the maximum possible power. Our target in this study is to present and discuss the different electric drive systems used in solar power trackers. And the other thing is to design and evaluate a solar drive system using dual axis tracking. And this is already made in our faculty in King Fahd University in Saudi Arabia. This is the block diagram for our proposed system. It consists of electrical source, the power electronic converter that is going to drive the motor, and this motor is connecting to the actuator, which is here used in this study as linear actuator, which is preferred from developers. And we need position sensor in order to reflect the position of motor and use a digital controller. We use here local controller Arduino Uno kit in order to collect the signals and give the proper pulses for the power electronic converter. So this is simply the controller and actuator for one of the angles. Assume this is for azimuth angle, and we need another one for elevation angle. So for sure we will have only single controller for both of motors, and this is called local controller. And we need to communicate between all of heliostats using master controller. And the target of each controller is to calculate the angles of each heliostat in order to reflect the sunbeams accurately during the day. Here we have, this is considered the field of the solar power tower. As you can see, we have lots of heliostats around, arranged around the tower. Okay, each heliostat has to be controlled separately in order to achieve certain reflecting angle, certain azimuth and elevation angle. So each one of the heliostats, mainly the construction of heliostat is like that. We have a base, we have a drive system here, we have the frame structure which will carry our mirror. So we need to move these mirrors in 3D motion in order to reflect the sunbeams on the target all of time. In the right-hand side here, we can see our prototype, which is made on the rooftop of electrical engineering department in our faculty. It's made all in KFUPM laboratories, and this one photo during the operation. And here we consider this part here as a target. In our work, we consider only the tracking work. We are not going to consider fluid and mechanical or thermal analysis, because we are going to focus only in electric. In order to reflect the sunbeams accurately, we have to use an accurate algorithm. So this is our solar position algorithm we have used in order to calculate the elevation and azimuth angles accurately for our heliostats. I'm not going to discuss it here in details due to the time limitation. However, all of the discussions about the mathematical model are described in details in our paper. We use this model and programmed this model onto an Arduino kit, which is the local controller for each heliostat. And now each heliostat will calculate its own angles in order to reflect the sunbeams in the air. Now, let's go to the most important part of the heliostat, which is the electrical drive system. There are lots of studies have been implemented before that have classified the cost or make cost reduction for heliostat, and we could find that the heliostat, the drive system contributes around 35% of the cost of heliostat. So it's a very important part to be investigated and improved in order to reduce the cost, in order to improve the system performance. For that, we take care about the electrical drive system here in this construction. We have two main drive systems. We have DC drive systems, we have AC drive systems. This is just a summary for what we have discussed in our paper. For DC drive systems, we can use the field-based motor like DC shunt motor or separately excited motor. However, separately excited needs two supplies. Shunt motor has only one supply. Also, we can use the permanent magnet DC motor, and actually, this is the most one used in industry that any developer are preferred. Okay. However, in our study and in our work, we could find that the harsh weather conditions in Saudi Arabia is not preferred to use the permanent magnet DC motor as a common motor in this application because of the demagnetization and small lifetime of magnets for this type of motor. So we don't like to use permanent magnet DC motors in harsh weather conditions, and this is one of the main issues we could find in our study. For the power circuits that can be used for DC motors, we can use rectifier, AC to DC converters, and we can also use DC to DC converters like 4-quadrant DC chopper. It depends on the availability of the source. And for the control technique, we have many control techniques that can be used also for each circuit and each motor. The other type, we can classify this motor as a special type of motor, like stepper motor, or we can classify it also as a DC drive system. Stepper motors also are used in heliostats drive systems, either permanent magnet stepper motor or variable reluctance stepper motor. And the main circuits that are used in these stepper motors are DC to DC converters based on switching devices, GTO, IGBT, MOSFETs, or any transistor switch. And the control technique that are used with stepper motor are based on phase current control with pulse width modulation. The last type of drive system that are used in solar power tower is AC drives. We could find that induction motors are used in solar power tower. However, we couldn't find any study using synchronous machine in that device. We don't know why it's not used up till now, and we prefer using synchronous motors in a lot of applications in electric vehicles and other applications. However, it's not used yet in this solar power tower applications, and this point needs investigation. Regarding the power electronic circuit that can be used for induction motor, we can use the back-to-back converters, back-to-back thyristors or triacs for making for volt control of induction motor, and this is called phase control. And this is not preferred a lot in industry. However, this is called considered as a cheap solution. But the voltage source inverter is preferred as back-to-back converter because the variety of control techniques that can be used, like PWM techniques, like vector control, like predictive control, and so on. For our experimental work, this is the basic circuit that we have used. We used 4-quadrant DC chopper, or called full H bridge, and it consists of 4 semiconductor switches. We used silicon carbide MOSFETs in this circuit. We implemented our circuit in laboratory. This is the PCB after implementation, and this is after inserting and soldering all of the components. It's based on advanced wide bandgap silicon carbide switches, and we prefer to use this technology, by the way, because of the higher efficiency of silicon carbide based converters compared to conventional silicon IGBTs or silicon MOSFETs. And this is, by the way, suitable or preferred in harsh weather conditions like what we have in Kingdom of Saudi Arabia. This is our implemented heliostats. We implemented 2 heliostats on the rooftop of our department, electrical engineering department. And we considered here this part as a target. And as we discussed discussed in the beginning. We are not going to make thermal analysis or fluid analysis or like that. We just care about tracking. So our purpose here is to achieve accurate tracking, and after that, analyze the performance of the drive system itself. As we can see here, we have several photos for the two heliostats during several times in the day. And we can find that all of the figures, all of photos here, the two heliostats are reflecting the sun beams on the same targets, which reflects now that our tracking system and drive system is accurate. For sure, this is now a small prototype. In our project, we have a plan to make a large prototype on a large area, but this is preliminary model or preliminary prototype for our work. We analyze the performance in terms of the accuracy of the drive system. So we made simulation and we get the experimental results for the azimuth and elevation angle for our drive system. And as we can see, that simulation and experimental results are in a well agreement. Finally, as a conclusion, a summary for electrical motors and recent advancement in power electronic converters are discussed. A complete DC drive-based heliostat prototype is designed and implemented in KFUPM laboratories based on advanced wide bandgap silicon carbide semiconductors. We could see that the results are well matched for azimuth and elevation angle, for which reflect that the dual axis tracking has been fulfilled accurately. The experimental results and simulation results are in a good agreement, as we said. Now, the current and future work. For the current work in these steps, now we are working in many things. Firstly, the current work is measuring the system performance in terms of drive system efficiency based on the different semiconductor technologies. Now we use silicon carbide. What about gallium nitride? What about the difference in or saved energy compared to conventional silicon IGBTs or MOSFET? We are making this work now. Also, the effect of harsh weather conditions in Saudi Arabia on the proposed system, because as we discussed, permanent magnet DC motor lifetime is changing or affected by the thermal stress in the weather conditions here in Saudi Arabia. So what are the proper motors that can be used instead of permanent magnet motors? This is also in our plan. Finally, the effect of harsh weather conditions on the drive system lifetime. These are the current and future work of our project. Thanks a lot, and you are welcome if you have any questions.
Many thanks, sir, for your presentation. Someone wants to make any question? Well, not in the room. We will see. Well, we will start with the next presentation. 317, design of LLC resonant converter for powering a, yes, from the previous one session was a lost presentation. Design of a LLC resonant converter for powering a PEM electrolyzer. Mr. Vitale, you can start.
Okay, thank you, Mr. Chairman. I'm sharing my screen. I hope you can see it. Okay. Can you confirm it, please?
Yes, you can start, please.
So, okay. So, this contribution will describe the design of a LLC resonant converter for powering a proton exchange membrane electrolyzer. It has been realized in cooperation with the University of Polymer and the Université de Lorraine in France. So, this paper addresses the design of a LLC resonant converter to supply a proton exchange membrane electrolyzer. The electrolyzer requires a low voltage and high current, a reduced doped output voltage ripple and an overdamped dynamic behavior of the converter to avoid voltage overshoots. The design aims to compare the advantages and drawbacks of a LLC converter for this application and to address specific improvements. So the presentation is organized with an introduction, a description of the hydrogen as a green energy vector, the design of the converter, results and conclusions. The research activity aims to promote research on sustainable and clean energy conversion system. There are two special issues available with a discount on the fee, so if you are interested on them, please contact me. There are many hydrogen applications of interest. In transportation, for example, when the hydrogen can be used to supply fueling station. As energy storage, hydrogen can be used like an energy vector to face, for example, intermittent energy disturbances when renewables are used. In power-to-gas application, it consists of converting hydrogen through the methanation process into a green natural gas. And then finally, in industry. The best solution would be to adopt always renewable sources to produce hydrogen. So, in principle, we could use energy coming from solar energy, wind sources, or hydro plants to produce hydrogen, and then after storage, it could be used in transportation, storage, power to gas, and industry. Unfortunately, at the moment, only a small part of hydrogen is produced by renewable. Very high part, about 96%, is produced by fossil fuels. So in this activity, we try to promote this kind of solution, mainly based on the power conversion. So in particular, the path includes the water splitting by electrolysis and the use of proton exchange membrane electrolyzer. There are different types of hydrogen. We can distinguish between gray and green hydrogen. So since the usage of fossil fuels produces low purity of hydrogen with high concentration of harmful greenhouse gases. Among many hydrogen production methods, eco-friendly and high-purity hydrogen can be obtained from electrolysis of water to produce pure hydrogen and oxygen. But however, hydrogen production efficiency through water electrolysis is very low to be economically competitive due to the high energy consumption and low hydrogen evolution rate. Probably it is a reason for which the production is mainly performed by fossil fuels. On the other hand, the use of polymer electrolyte membrane is very interesting, since we can note that as input there is water, and then it is split into protons and oxygen and electrons, and then they are separated by recombinated into a biatomic molecule of hydrogen. So we have in input water and as output hydrogen and oxygen. So for this reason, we can consider this kind of hydrogen a green hydrogen. If we want to adopt renewable sources, we need to a high step-down conversion ratio. So this is the reason why mainly electrolyzer require very low voltage, and on the other hand, photovoltaic and wind turbine and so on give us high voltage. Basic topologies usually show a very poor efficiency for high step-down conversion. And for this reason, different topologies have to be considered. And people of interest is to use resonant converters. The traditional converters exploit resonance mainly to achieve a zero voltage switching in power switches. And traditional topologies can be divided in series resonant. The first topologies is a voltage partitioner mainly. So its gain is. On the other hand, the parallel resonant converter requires usually a large amount of current. But if we consider to adopt another inductor, we can recognize the two different resonant frequencies, and we can choose an operating frequency that depends on the load. In this way, the designer has a In addition, if we use this operating principle in a circuit, we can build the LLC converter by a square wave supply. It is formed by two MOSFETs, giving a square wave as output. The resonance circuit, which exploits the magnetizing inductor of the transformer. So it is not an additional component, but it is included into the transformer, of course, and then a rectifier and out filter to supply as the output the DC low voltage. The analysis of this circuit can be performed considering only the main switching frequency, like a sinusoidal one, so that gain function can be derived. And we can note that it depends on the switching frequency, the ratio between the two inductors, and on quality factor. So it gives the designer the possibility to choose among many gain curves. In particular, it is better to work with a linear curve so that increasing switching frequency, the gain can be decreased. So it is a good way to regulate the output voltage. For our study, we considered QL300 PEM hydrogen generator that is produced by Fuel Cell Store. This device used as a load requires 5 volts that correspond to a DC current of about 45 ampere. Based on this, the constraints of the converter are an input voltage in the range between 300 and 320 volts, a rated power of 225 watt, an output voltage ranged between 10 and 5 volts, a maximum of current of 45 ampere, voltage ripple lower than 120 millivolt, and the switching frequency between 100 and 150 kilohertz, and finally an overdamped response. The switching frequency is useful to preserve the DC component of the output current so that a reduced ripple both in frequency and in amplitude is given to the electrolyzer, and the overdamped response is required to preserve the electrolyzer from overshoots. Based on the choice of the components, we worked with the blue curve, ability to exploit linear gain, a decreasing linear gain. And now, okay, we can see some results. Starting from the output voltage, in the worst case, meaning at 150 kilohertz, with an output voltage of 2.65 volt, the output voltage ripple is about 50 millivolt. This is a good result since the output voltage is practically DC voltage. The resonant circuit allows to achieve the zero voltage condition on the power MOSFETs, so they can commutate when their voltage is null. So it is very useful to minimize switching losses. concerning the output diodes rectifier, they can commutate with null current. This condition, of course, in correspondence of the crossing point between and the magnetizing current. The current of the resonance circuit and the magnetizing current. So it is useful to minimize the reverse recovery losses. And finally, the response is overdamped as required. So in particular, when the voltage is varied with the step solicitation, no overshoot can be noted. As for the losses, the topology allowed to minimize losses on transformer, on the inductor, on the power switch. The conduction losses on output diodes remain quite high, since they are mainly due to the drop voltage on diodes. So this is the reason why the efficiency power is about 65%. Summarizing the results, a LC converter with high step-down ratio to supply a proton exchange membrane electrolyzer has been designed and verified. The with high switching frequency, minimizing switching losses by 0 voltage switching. A small output voltage ripple is obtained, and the converter shows an overdamped dynamic response. On the other hand, a relative high amount of losses is due to the output voltage rectifier. As a further improvement, the losses due to the output voltage rectifier will be reduced by a synchronous rectifier based on low on MOSFET. In this case, an increase of about 10% of the efficiency is expected with this upgrade. So this is all. I would like to thank you for your kind attention, and sorry for the last inconvenience in the last session.
Many thanks, Gianpaolo Vitale. If someone has any question for this presentation, well, not in the room. We will see. Well, then we go on with the next one, oral presentation, 267, clustering technique for scenario reduction in post-energy transition voltage, deep assessing. No, todavía no, ¿no? La 267. Okay, we will go on with clustering technique for scenario reduction in post-energy transition voltage, DIPS assessment, from the Department of Electrical Engineering of Eindhoven Technical University, the Netherlands. We will try to share the presentation.
Hello, Mr. Chairman.
Yes, perfect. You
Can you hear me?
You can start, please.
Buenas tardes. Good evening, ladies and gentlemen. Can you see my screen?
Yes, go on, please.
Yeah.
If you are ready, you can start. We have lost the sound.
Hello, could you hear me?
Yes, please start again if you can.
Yeah, sure. Hello, everyone. I'm Roosevelt Orsade, a PhD candidate at Eindhoven University of Technology. I'm presenting you the result of my research together with Dr. Jeroen van Was, Dr. Vladimir Chuk, and Professor Chef Koban on cloud reduction in post-energy transition voltage dip assessment. In this presentation, first, I want to talk about the motivation behind the work. Then I will discuss the use methodology and the result. And finally, I will conclude the presentation with the conclusion and future works. Our main motivation in this work was to investigate the impacts of energy transition on voltage dips. Voltage dips as power quality phenomena can have huge impacts on the clients of the network. Therefore, the Dutch grid code defines four residual voltage and the duration. Also, Dutch grid code stipulate limits for the number of can have in their network, and these limits transition. But the important question is how to define the energy transition. In the Netherlands, the Transnet develops 10-year investment plans every 2 years. One of the most recent one is the investment plan 2020, or in short, IP 2020. The IP 2020 foresees 3 different trajectories for electric grid of the Netherlands for 2030. The first one is the Climate Agreement, or CA. It is foreseen that this has all the requirements for the Paris Climate Agreement. The second trajectory is the Fundamentals for System Integration, or FSI. In this scenario, it is assumed that the more renewable energy sources will be developed within Netherlands, and electric load will increase due to higher number of electric vehicles and more electricity in use in other sectors. And finally, the last trajectory is the Alternative Transition, or AT, in which lower amount of renewable sources are considered in comparison to KA, but more green technologies such as power to gas are foreseen. For each of these trajectories, 3 different 2020, 2025, and 2030, as are shown in the right figure. And for each of these reference cases, market simulations are done. The market simulations are used to translate the high-level description for each of these reference cases to 8,736 operational scenarios for each hour of the target year. The market simulation defines the dispatch of the generation and load based on their fuel type. Considering 8,736 different scenarios for each reference case, demands a huge amount of computation and post-analysis processing, which make this analysis undoable. For it's essential to reduce the number of scenarios to a limited set of the most representative states of the grid operation in future. Before talking about the proposed scenario reduction technique, it's important to define the representative indices for each hour. These indices help to distinguish between the hours based on their appropriateness for the aim of this study. As mentioned earlier, the main goal of the research is voltage assessment in future network, and therefore the most important factor that can alter the assessment result is the changes in the system strength with regards to the short circuit level. As changes in the load and generation pattern, as well as grid developments can alter the short circuit power for various nodes, we have defined 3 different indices. First one is the nominal power of all in-service synchronous generation, regardless of their operating set point, because this unit can hugely participate in short circuit power. The second one is the aggregated load of the Netherlands. For this purpose, we have considered the whole electric system of the Netherlands as a simple node, which has various inputs and outputs from perspective of the power flow. The inputs are the synchronous generation, renewable generation from solar PV, onshore and offshore wind farms, also the power import over the AC high voltage connections to the adjacent grid, and finally the import over the HVDC connection. And the outputs are the load of the clients in Netherlands, the export over the HVDC and also HVAC to the neighboring grids. The aggregated load is calculated by summing all the outputs for each hour together. And the last index is the non-synchronous penetration index, which is majorly adopted from an index colleague in our grid, the TS of the Netherlands. They call this index SNSP. The higher values for non-synchronous penetration index shows lower amount of in-service synchronous generation with comparison with the renewables. Here we can see this of these three indices for 4 reference cases, namely CA 2020, CA 2030, AT 2030, and FSI 2030. It can be seen that despite the lower load aggregated in the KA 2020, with all the 2030 scenarios, we have more synchronous generation in service for almost all hours of the CA 2020. By comparing the in-service synchronous generation 2030 cases, we see that the FSI has the higher values in comparison with KA 2030 and AT 2030. And it can be explained by the much higher foreseen aggregated load for the FSI 2030. And finally, by comparing the non-synchronous penetration index in the right figure, we can see that a much higher share of the aggregated load is foreseen to be supplied by the sources that are interfaced to the grid with power electronics. For each reference case, we have 136 operational scenarios. For example, in this figure, you can see those points for the KA 2020. And now the question is how we can reduce this huge number of scenarios into a limited set, but a representative number of cases. In this work, we proposed K-mean clustering for our approach. The first step in our approach is to build the dispatch values per each generation unit within the Netherlands. For this aim, we need to convert the market simulation values to per generation unit values based on the mass run obligations and also the priority of each generation unit. Then we calculate the proposed 3 indices for all the hours of the year for that reference case. Afterward, we run the K-mean clustering algorithm for different number of clusters from K equal to 2 to K equal to 100. Based on the values for variance explained, for each of them, we can select the optimal number of clusters. In this work, we assume the 90% threshold. For more details on the K-mean clustering and optimal number of clusters, you can refer to the paper, and I'm not going to explain them for the sake of time. Then, we are going to filter out the most common synchronous generation pattern. The typicality of, or the most common state is going to define based on the hours that a synchronous generation is in service. So if it is for more than 4,000 hours of the year, we consider it as a typical one. A very important note is that the voltage dips analysis are not interested in rare extreme conditions, but we prefer to focus on the most typical situation, as voltage dips are highly expected to happen in the most typical grid states. And finally, to just pick some representative cases, we are going to use the Euclidean distance to find the closest scenario to the centroid of each cluster. So here you can see the result of our method for the 8,736 operational hours of the KA 2020. The first step is to apply the K-mean clustering for the lowest number of the cluster, which has the 90% of variance explained. In this case, we had the K equals to 8, and you can refer to the paper for more information about this one. With regards to the values of the, you can see those 8 clusters with different colors in this figure. The most frequent this you can see that the number of cases has reduced to a limited one. So here we have 8 clusters of data, and each of them only considers the most typical status of the system with regards to this in-service synchronous generation. And finally, by considering the closest value to the centroid of each cluster, these are the final result or the peak scenarios. To conclude, considering all the foreseen grid states after energy transition makes a futuristic voltage dip assessment undoable. Therefore, the implemented clustering method has representative cases after energy transition with regards to the defined indices. However, in order to compare the impacts of various energy transition scenarios, it's important to have peer-to-peer set of clusters for all the various energy transition scenarios. And for sure, there is some extra room for further research with this regards. Thank you so much for your consideration.
Many thanks, sir, for your presentation. Someone wants to make any question for this presentation? Well, then we follow with the next one. This will be in face-to-face. Solar Carport from the Alternative Energy Sources Knowledge Center, Budapest, Hungary.
Thank you, ladies and gentlemen, last but not least. So I introduce you our experiment. It's called Solar Carport. So first, I introduce the environment, why do we need it and why we have done it. And then at the end, I show the innovative product. So as you know, the global electric vehicle sales emerging, and in the next decades it will be more than 10 times much electric car in the world. The electric cars, the main element of the electric cars, electric vehicles, is the battery. Mainly now it is a lithium-ion battery. So the battery demand of the car increasing too. Of course, there are other purposes, not only the electric cars, the electric buses, and the general electric storage, but the main element, main part is the car battery. Okay, when you have a car and we use it, it has a lifetime. And maybe it can be extended a little bit, but practically battery can be used for 6 or 8 years. But what can we do after the usage in the car? So we can have another purpose. It is the global storage capacity, so storage for energy, not only in the car. It is another market, and up to this time it is an independent market, so there are some batteries for the electric vehicles and other batteries for the energy storage. And also an increasing share of this market is the residential storage at home. We have to know that footprint, CO2 footprint, and also the energy footprint of the batteries is roughly proportional of the storage capacity. So 30 kilowatt hour battery requires about 21 kilogram of CO2 emission per month in their life cycle, and in a 100 kilowatt hour battery has about 3 times more. It is too much, and we should somehow reduce. But the technology is limited, and it is not so easy to reduce. How can we reduce this emission? If we cannot reduce the emission, we can extend the months, extend the lifetime. So we arrived to the solar carport idea. All the elements are known. The carport, for example, here is a carport also in the Almeria University. It is also a solar carport because the carport is covered, the roof is covered by solar panels. But another aspect, the emerging number of the second-hand, the emerging number of the used electric vehicle batteries. So, our innovation, or 4-in-1 innovation, we made a carport that covered with photovoltaic panels, and it's capable to charge electric vehicles and also store the energy in the second life or second-hand electric vehicle batteries. Here you see the prototype was realized in Budapest in Óbuda University. It has a roof holder structure, and it is relatively simple, and it is covered with photovoltaic panels. 24 pieces of panels, it's more than 7 kilowatt peak, and it is the second generation semi-transparent panel, so it is it looks quite good, and it produced not only electricity but also some shading for the car, but it is not a closed roof. Also, the air can flow between the panels, and also some light is emitted in. So we have EV charger, electric vehicle chargers. It is too simple or traditional wall box, but it operates in the charging mode 3. So it is not the fastest. It is not the fastest charging mode, but it is capable to charge up to 22 kilowatt. So in case of the normal car, it means during half or during 1 hour you can have a full load. The charger can be started by the RFID card, and also we have the inverter. So the panels, photovoltaic panels, directly connected to the inverter. It's a 8 kilowatt inverter, and we have a smart meter, and the heart of the system is the battery management system, the Victron battery management system, and through this system we can connect the different elements of the system. So one element is the storage. You can see in the middle. This is the storage. Another is the photovoltaic generation. And we can have input from the normal network, and of course there is the load. There is the charger, the car charger. And another important element is the battery. But this battery is a second-hand battery, and we use Nissan Leaf battery modules. It is the second generation modules, about 6 years old, and here are the stacks. Each stack contains nine battery, and we have to know in the car the batteries are connected serially, and it produces about 800 volts. But we connected it parallelly, so the system voltage, the battery system voltage in our system is 48 volts. Of course, there are many different protections against electric shock, overvoltage, from external overvoltage and overcurrent. We have special cabling. Here you see the operational mode. So there is a car. The car can be charged directly from the photovoltaic energy. The car can be charged from battery. The surplus energy can be stored in the battery, and in case of overcharged mode, we can feed back to the network, or in case of more need, we can charge the car also from the network. And this is the electric scheme, and also some view of the system, upward, downward, inward, outward. And you can see it is a very simple, not so special building, but it becomes jewelry of the building, and it gives a very nice shadowing in the sunny days too. So the project was realized by some partners. Industrial partners was one photovoltaic system settling company, premium Napalm company. The other partner, and we gave our knowledge and the site, the university, and it was financed by an European urban mobility program. And it is very important, this product, this prototype, is recommended to another project. It is called EUKI project, European Climate Initiative, and it's dealing with how to improve, how to set up more and more photovoltaic system, small scale system on the roof of the houses in Budapest, in the city, in the city, and also in the suburbs too. In this project participates the Budapest municipality, over the university, and also an industrial association. And the outcome of the EUKI project, on the one hand, a cadastre, the potential, how much a photovoltaic system can be or could be set up in Budapest. These are hundreds of megawatts. And the other outcome are the typified solutions, different typified application that can be realized in in a large number. And one of such recommendation, one offer, is this solar carport. This is a small scale solution for suburban households, for up to 5 or 2 times 5 kilowatt. But it can be also recommended for a large parking lots. If there are some public parking places where hundreds of cars can be parked, and this n times x kilowatt hour storage capacity based on second-hand electric vehicle battery can be also a good solution. because these batteries can be used for the next years. The normal lifetime is 6 to 8 years, and we can extend the lifetime, the usage of this battery for another 6 or 8 years. And this is a contribution for the environment protection, because we don't have to throw it away, but we can use it in the same amount of the time. So an acknowledgement for the EU key project and the urban mobility project, and thanks for your attention. Any question, please?
Sí.
Thank you. Congratulations for the project. I have two questions. On one hand, I would like to ask you why you have chosen good for the structure. I mean, does it add any value because of being wooden? Is it because of money, because of aesthetics? And the second question is if it's worthwhile that the panels are bifacial instead of monofacial, in terms of investment and added value. So wooden and bifacial. Thank you.
Thank you for the question. So the basic idea, this solar carport idea, to have photovoltaic, a roof, a charger, and a storage. So the element can be different solution. So the wood holder is one possibility, but it can be also a metal structure and any other structure. So the wood is not so important, but yes, but it depends on the country, it depends on the market, because I think so to make a prototype, it's far more cheaper in my country by wood than to make a steel structure. Of course, if there are hundreds of applications, in that case, a serial of metal structure can be cheaper. The other question, and also I think so in the environment, it's a very, very rigid environment, a lot of concrete, and everything is gray. So the wood makes a little bit looks a little bit environment friendly. Another, this is not a bifacial panel, of course, but if we use bifacial, it depends on, because we want to use it as a cover, and in that case we could use some reflection from the ground. But it depends what is the covering of the ground. If it is a white sand, it is recommendable. If it is a dark or a black color, in that case, no. It can be an extension in the future. Yes, it is. We plan to make also some bifacial application, and it is strange because this company, this Solitec, it is as I know, it's a Lithuanian company, produce also bifacial panels. So maybe in the future we shall apply it. Thank you. Yes. Yes. Okay, thank you. Thank you once more. take away.
Well, we go on with the next recorded presentation, video presentation 250, I think. Where is this? Yes, technical and economic feasibility study of solar plant on a commercial surface in Azogues, Ecuador.
It's a pleasure to be here with you. My name is Martín Bermeo. I'm an electrical engineer. I'm representing Grupo de Investigación en Energía from Universidad Politécnica Salesiana sede Cuenca, Ecuador. I'm going to talk about the next paper, Technical and Economic Feasibility Study of a Solar Plant on a Commercial Surface in Azogues, Ecuador. Let's get started. Let's get started with a short introduction. In Ecuador, there is little experience in the grid connection photovoltaic system. The figure 1 shows some previous studies in the country. There are 8 projects, but only 2 are feasibility, the Project Cuenca and Project Quito Los Bancos. Currently in Ecuador there is the Regulation 00318 of ARCONEL. This regulation conditions the forum implementation for consumers that have PV generation system located on roofs, housing areas, or buildings for users in either low or medium voltage. The commercial center has at least 2 characteristics worth studying: the available roof area and the demand curve. This project is located in Ecuador, province of Cañar, in the city of Azogues. In the figure 2, we can see where is the La Playa shopping center in Ecuador. In the next illustrations, we can see how is the building of the La Playa shopping center in Azogues, Ecuador. Let's continue with another point of the case study. By means of on-site inspection of the low voltage network, it was deduced that the power installed in this commercial building to be analyzed is 66.46 kilowatts peak. There are no cool rooms or 24/7 loads in the site. The maximum consumption requirements were defined by taking measurement using a power quality record. The data sampling was carried out between December 4 and December 11 from the year 2018, resulting in the following active power curves. There are no meteorological stations in the sector to access the daily irradiation data present, so 3 options were studied to obtain the data: the solar atlas for electricity generation in Ecuador, the NASA database, and finally software Meteor. We used the last option. For this study, the value of the month with the lowest radiation corresponding to July, with 223 watts square meters. The roof of the building is made of aluminum due to the presence of polycarbonate sheets on the roof. The available area was reduced in 246 square meters, leaving a remaining total useful area of 1,733.72 square meters. Let's continue with the design of the solar plant. Based on the measurement and installed power data, we are going to design a solar plant with a nominal installed power of 60 kilowatts peak. The regulation 00318 from ARCONEL limits the installed power capacity to less than 1000 kilowatts peak. Now we can see in the table number 1 the different characteristics of the solar power plant. We have an occupied area of 313.87. We use 156 panels of 400 watts. We have 3 investors, and we have the power year we array 20.8 kilowatts. We have an installed nominal power of 62.40 kilowatts peak. The annual year energy produced is 23,695.26 kilowatts hour, and we have a plant factor to 18.03%. The monthly energy produced are divided on the 12 months of the year. The system performance of each month is around 8%. Architectural integration. In this case, the ideal is to make 3 groups of photovoltaic panels, excluding the area of polycarbonate sheets for natural lighting. In addition, it is advisable to have a symmetrical distance between these groups for the future circulation for purposes of maintenance and inspection. Now, as you can see here in the figure 8, the different groups on the building roof. After that, we use the Lumion software to simulate the architectural integration. We can see the 3 groups of photovoltaic panels on the roof of the building. Figure 9 and figure 10 shows the top view simulated. Let's move on to the next point, production and demand analysis. Solaris PV show the next information. Highest production month corresponded to October with 8,929.24 kilowatts per hour. The lowest production month corresponded to July with 7,135.58 kilowatts per hour. The plant will have an annual yield of around 94,000 kilowatts per hour. Based on the invoices obtained from the distribution company, it was possible to know that the month of highest energy demand was June, with 24,000 kilowatts per hour, while the month of lowest demand was November, with already 20,000 kilowatts per hour. In the year 2018, the energy demand of the shopping center was around 237,000 kilowatts per hour. The next is the net energy values per month. Net values are the difference between the energy billed and the energy generated by the PV systems connected to the grid. The reduction in demand with the presence of the solar plant changed from 236,000 kilowatts per hour to 143 kilowatts per hour. Based on this, the hourly demand will be reduced over a year by 35.54% with the Dyson rooftop solar plant of 62.4 kilowatts peak. Cost of the photovoltaic plant. Based on invoices from local distributors, the total value of the installation and purchase of material was estimated at $70,000, with an estimated price per installed watt of $1.11. Invoicing of the installation. La Playa Store Shopping Center is a commercial consumer at medium voltage with a hourly demand. The following items to be considered are detailed in the tariff specification for the year and are shown in the table number 3, cost of components and installation of the photovoltaic plant. Based on these items, the total bill by the distribution company for 2018 is around $29,000. The tables 4 and 5 shows the annual energy billed values for the hourly rate of 8 to 22 o'clock and 22 to 8 o'clock. The annual cost of electricity tariff is $21,387.44, and the annual cost electricity power rate is $913.62. On the other hand, the annual cost of electricity with the solar plant in operation during the hours of 8 to 22 o'clock is $12,400 $486.40 per year. The table 7 shows the annual cost of electricity between 8 to 22 o'clock with the grid-connected PV system. As you can see in the next figure, it shows that the total annual billing cost without grid-connected photovoltaic solar plant paid by the user is $29,095.2, while with grid-connected photovoltaic solar plant, the total annual billing is $90,602, reducing a total of $9,492, 1 year representing a reduction in cost of 32.63% with respect to a normal annual billing cycle. Final C evaluation. We proceed to the calculation of internal rate of return and net present value. It is important to note that it considers 20 years operating period according to ARCONEL 00318 regulation. In the illustration, nothing than starting with the 5th year there is a positive remnant, $2,800, until the 20th year with a positive remnant with $361,000. To perform the internal rate of return and net present value, we use the next information from Banco Central del Ecuador from the year 2019. As you can see in the illustration, the calculated NPV value is positive. Therefore, it is feasible to execute the project. The figure 16 shows the calculated internal rate of return value projected to the 5th year with 1.30% and to the 20th year with 23.21%. In the next illustration, we can see the financial overview. The information most important are payback time 5 years, net present value $133,000, internal rate of return 23.21%. Now we are going to see the discussions of the project. As a consequence of the location, there is regular radiation throughout the year. The LaPlay store facility is categorized as a medium voltage commercial consumer with hourly demand. With a photovoltaic system installed in covering, it will manage to reduce 32.63% of this invoicing. This is an important detail since the shopping center attends 12 hours from 8 a.m. to 20 p.m. and does not have refrigeration systems or cool rooms that will cause an increase in energy consumption. This case be considered a coupling between demand and photovoltaic supply. The photovoltaic generator has about 10 hours of sunlight, only no longer providing power to the facility from 18 to 20 p.m. On the night, the installation will consume energy entirely from the distribution grid. Continue with the discussions. The annual energy reduction represents about 32.63%, which is a quarter of this normal billing. Therefore, according to the estimated economic analysis, the investment recovery will be realized at the end of the 5th year. The price per watt installed is around $1.11 due to total cost of the installation and the power supply are around the same value. And finally, we have the conclusions of the project. The development of the target feasibility analysis for a shopping mall will serve as the base for any future solar generation project in commercial surface, because it is a sector where large amounts are invoiced for energy consumption. With the grid systems in commercial areas, it is proposed to reduce the value on the invoices to recover the investment. It should be considered that they should adjust the parameters according to their case studies such as geographic location, radiation, energy demand, power supply, area availability, among others. The photovoltaic panel should be installed coplanar to the surface so as not alter the aesthetic and structure of the roof of the installation. The orientation of the panels will vary according to the point where they are in the structure. This research was done under the guidelines of ARCONEL 00318 regulation that currently rules the national grid interconnection. However, soon a new regulation is expected for photovoltaic microgrid interconnection. Thanks for your attention. It was a short resume of the paper, and waiting the next edition of ICREP. I see you the next time. Thanks.
Hello to everyone. In the framework of Micro Solar Project, which is funded by the finally, I'm going to present the main findings we obtained from the an important role in the supply of many electricity-driven demands like lighting, water, pumping, and so on, linked to the provision of social services, economic growth, and improved quality of life in isolated population settlement and France. Nevertheless, the use of solar thermal energy in this context, to supply heat instead of electricity, is still a scarcely explored niche. However, the recent interest by solar companies, research centers, and technical associations in the so-called solar heat for industrial processes field allows accounting with many operative references on solar installation using concentrated thermal solar collectors. So this is the framework of Microprot solar project, whose main objective is to develop analysis and decision-making instruments that justify and promote the implementation of solar technologies for self-sufficiency in isolated productive enclaves of Chile, Mexico, and Spain. And well, based on this, the main objective of this paper is to contribute to the justification of the implementation of solar heat for industrial processes facilities to the ongoing initiative related to the use of renewable sources in traditional population settlements and industry. Specifically, we carry out an economic assessment of the use of linear Fresnel solar collector for the heat supply in traditional fruits and vegetable processing industries in Almeria's province. So let's start with the material and methods. First, we are going to observe the overall contents and solar resources of the location under the study. As I said before, we studied the province of Almeria, which is located in the southwest of Spain. The main economic activity of Almeria's province is intensive agriculture, which constitute an extremely productive and high-income activity. In this study, we identified several companies related to canning and traditional crops processing. You can observe these companies here in the map. They are the green points. And all of these companies are characterized by their remoteness from the main energy supply lines, also by their small range demand, and by the coincidence of using fossil fuels as the main thermal energy source. It is important to remark that in the map you can observe also the gradient of irradiance, which was calculated based on a geographical clustering according to the officially established cultivation regions in Almeria's province. You can observe here the data used to calculate the gradient for each of the cultivation area up and for each of the months of the year. In particular, we studied one of the aforementioned companies. It is a preserved vegetable facility with products mainly related to the tomato. In this figure, you can observe the thermal demand profile of the company per month. And it was obtained based on preliminary information cross-checking, and the accumulated demand along the year was 101,510 kilowatts per hour. Based on this profile, we generate 3 additional case studies. Case study 2 was generated considering that the industry works at maximum power during the entire year. And then case study 3 was generated considering an industry with the same profile that case study 1 but with double production. And case study 4 was generated considering an industry with the same demand profile than case study 2 but with double production. As power technology, we use the specification of a linear Fresnel solar collector designed and manufactured by the Spanish company Solato. As integration scheme, we use the scheme that you can observe in this figure, in which the solar field was connected in parallel with a conventional boiler that was used as backup. The technical specification of both the linear Fresnel solar collector and the integration scheme were obtained from recipe software. So moving now to the results. First, I'm going to present the way in which the simulation were performed. We used to carry out the simulation 2 different softwares. The first one is recipe software. In this software, we introduce information about the industry, like the thermal demand, the location, the working temperature, and so on. And we also introduce information about the solar field configuration. Indeed, for each case study, we tested different solar field configuration, modifying the solar field size and the storage tank volume. Then we collect all the technical and economic information that recipe software provides for each case study, and we extrapolate this information to MATLAB. With MATLAB, we perform a long-term economic study considering different aspects like the fuel price, the maintenance cost, and degradation factors. And in this study we use metric like the cash flow and the discount payback period, which were represented using 3D response surfaces for each case study. So here you can observe the results related to case study 1. Just to remember, this is the thermal demand profile of case study 1. And this figure represents the cash flow as a function of the solar fraction considered, which is related with the solar field configuration we introduced in RESP software, and the lifetime of the facility. So we also represent here the surface of cash flow 0, so that the cut between this surface and the other one is actually the discount payback period of the investment. So for this case study, the best results were obtained around this region for a solar fraction around 0.17 and obtaining a discount payback period of 12 years. In case study 2, just to remember again, this is the thermal demand of case study 2. We performed the same study, and you can observe here the results. In this case, the best results were obtained around this region with a discount payback period of 7 years. All the results for all the case studies considered are summarized in this table, and it is important to remark that for case study 3 and 4, in which we consider industry with double production, the discount payback period were lower. 8 for case study 3 and 6 for case study 4. So let's see now the conclusions of this research. A solar fraction of around 66 and 82% could be reached for all the case studies. It was observed how, in general, the optimal solar fraction was lower for industry with large demands, for case study 3 and 4. All the case studies resulted in payback periods of around 6 to 12 years. In particular, for case studies with heterogeneous demand, the payback period was greater, around 12 and 8 years, than for case study with homogeneous demands, which was found around 7 and 6 years. This evidences how the homogeneity of the demand is a key factor in the economic performance of the solar field for industrial process system for the area and industries under study. The size of the industry was also found to be a fundamental aspect influencing the payback time. The results show how, for industry with higher demand, the payback period was less, around 8 and 6 years, than for industry with the same demand profile but with half of the demand, which was found around.
Anyone has any question in the room, because we have connected Professor Manuel Pérez? No. Then we follow with the last one, improving the overall thermal performance of parabolic truck solar collector using porous media.
Hi everyone, I'm Hussein Evadi, PhD student from the University of Politecnico di Torino, Italy. I would like to present you a research work conducted by our team with Professor Antonio Cami and Professor Laura Savoldi. The title is Improving the Overall Thermal Performance of Parabolic Trough Solar Collectors Using Porous Media. Through this presentation, after a short description of the role of solar energy systems in the world's sustainable development, I will discuss the concept of the work, followed by a description and modeling consideration. Then results will be presented under the hydraulics and thermodynamics point of view, and the main points will be summarized at the end. Sustainable Development Goals, also known as SDG, is a systematic framework to tackle the main global challenges such as poverty, inequity, and environmental degradation. As you can see, there are some headlines, each of which represent a specific topic to be addressed through this framework. What is of interest to this study is number 7, indicating affordable and clean energy. Having in mind that the climate change impacts are booming and today the world engulfed with such climate disasters, we must pay higher attention to the energy providers and resources. Clean and renewable energy resources are maybe the only alternative to the current pollutant fossil fuels. On top of that, solar energy is one of the leading technology for future energy, which is gaining unprecedented speed in development and dissemination. Concentrating solar power, or CSP, is one of the ways to utilize the thermal power of solar energy to generate electricity. As shown in this figure, the potential and number of installed power plants are rising, and this acceleration can have many reasons like efficiency enhancement and cost reduction. So increasing efficiency means any specific technique to whether improve the optical efficiency or boost heat transfer. Thermal enhancement techniques are usually cheaper and more effective. So with such methods, one can further develop the current CSP systems, helping to decrease its cost and promote its applications. Now, thermal enhancement techniques can be carried out through passive or active methods. In the active method, an external energy source is required to, for example, produce a turbulent regime and enhance the heat transfer coefficient. However, in passive methods, no force or external energy is used, and the heat transfer mechanism is improved with only internal effects. The integration of porous media with solar receivers is a passive method to increase the heat transfer area between the working fluid and the absorber, as well as breaking the thermal boundary layers through recirculation. Although these are the two important positive consequences of this technique, the rise in the pressure drop owing to the high friction between the fluid and porous media could be a sore point. Based on new findings, a novel porous matrix with a reduced pressure drop compared to the existing models can be developed using Rashek rings. As shown, the random injection of hollow cylinders with special dimensions and using a brazing material to solidify the structure will lead to the formation of this novel porous block. Therefore, in this study, a series of numerical simulations were performed to evaluate the viability of Rashek ring porous matrix for CSP applications. In this regard, the most common type of CSP collectors, which is the parabolic trough collectors, was aimed to be equipped with such technology, and its performance was analyzed through simulations. As it is indicated in the figure, a usual parabolic trough collector consists of a reflector that focuses the sun rays on a tubular absorber to collect heat on this area. Then, a working fluid, which is air in this study, passes through the absorber to convey the absorbed heat and transfer it to the next unit for thermal purposes. A tubular glass envelope is also included in these systems to minimize heat convection loss and improve thermal efficiency. Thus, in order to assess the effectiveness of Rashek ring porous media in thermal performance, a fraction of the absorber, glass envelope, and the working fluid were only modeled in the simulations. As a result, the absorber tube was assumed to be made of Inconel with an inner diameter of 20.6 mm and an outer diameter of 25.4 mm. A tubular glass envelope was also developed with an inner diameter of 30 mm and outer diameter of 32 mm. A total length of 70 cm of the absorber was chosen to be analyzed in this research. This fraction was then divided into two pieces, the first fraction with 50 centimeter smooth pipe where the inlet flow condition was set at the boundary conditions, and the second fraction with 21 centimeter, which was studied under two options. First, the smooth pipe with fully developed conditions and inlet and outlet boundary interfaces, and second, the enhanced pipe with the Rashegrig insert with again fully developed conditions at both inlet and outlet boundary interfaces. Please note that the connection between the first and the second fractions was made using the outlet data of the first fraction, such as velocity, mean bulk temperature, and turbulence criteria, to be input as the inlet data for the second fraction simulations. To apply an accurate thermal modeling, first solar radiation was simulated using the data in the literature, which led to the distribution of local concentration ratio on the tube wall. As shown on the right figure, the parabolic configuration of the reflector results in two peak values on the wall of the tube, roughly located at the bottom section. Please note that referring to the linear arrangement of the parabolic trough collectors, this distribution is longitudinally uniform. About the heat transfer mechanism applied to this modeling, I could say that, as shown in the figure on the left, solar energy emitted on the collector will be passed through the glass envelope and be absorbed by the tube. It should be noted that a fraction of heat is stored in the glass and causes the temperature rise on its wall. The energy absorbed by the absorber tube will be then conveyed to the working fluid, which is known as useful heat. On the other hand, considering thermal losses, we have several issues. First, it was assumed that the gap between the tube and the glass envelope is evacuated, so the convection loss between the tube and the glass cover was neglected in this study. However, the radiation loss between the tube and cover is taken into account and will be analyzed further in this study. Moreover, two other thermal losses applied in the simulations are the radiative and convective heat transfer through the cover to ambient. CFD study considering energy, continuity, and momentum equations was carried out using Star System Plus commercial software. The applicability of the software is well known, and many scientists have reported the high accuracy of this platform. One of the features that we employed was the district element method, or DEM model, to generate the packed structure and form the process structure with Rashegrig as the particles. Then, after the development of the geometries, a 3D conjugated heat transfer model was used, accompanied by temperature-dependent properties of the materials. Based on the previous experimental and numerical studies, an effective thermal conductivity of 2600 watt per meter Kelvin was set for porous media. A radiation model was also added to the simulations to predict the radiative heat transferred between the two surfaces of tube and the glass. As the fluid regime was considered to be turbulent, the realized K epsilon model with two-layer wall treatment was used through the simulations. The appropriate meshing was achieved after a grid independence study testing various base size of cells and the number of prism layers, and Y plus was finally obtained nearly 1 at the whole fluid walls. Table 1 shows the optimum number of cells achieved for our simulations. The high number of cells for the enhanced pipe comes from the fact that in micro-scale study of the porous media, each particle must have an individual mesh, and this results in high computational costs. Coming to the results, hydraulic performance showed that the procedure reduces the fluid velocity and causes some pressure drops. According to Table 2, the rise in the pressure drop could be maximized up to 1400% compared to the smooth pipe. From the zoom section in the left figure, rings could accelerate or block the air passage through the medium. Actually, where there are sharp corners or internal channels, air streams accelerate, while where rings are accumulated, air streams are blocked. Considering the thermal performance as the air passes through the pipe, temperature profiles develop, and as shown at 3 tube lengths of the first segment, the temperature of various collector components are presented. As it was expected at x equal to 0, the pressure absorbs the heat from the pipe wall and cools it down significantly. At x equal to 25 cm, thermal boundary layers are formed and the rate of heat transfer decreases compared to the inlet section. Reaching to the outlet interface, the temperature of the pipe rises due to the reduction in the temperature difference between the tube wall and fluid boundary layers. This further decreases the rate of the heat transfer and increases tube wall temperature. As the consequence, there is also a short temperature rise in the glass envelope, which indicates growth in the radiative thermal losses between the tube and the cover at the ending sections of the first segment. Totally, it can be concluded that in this method, the penetration of heat into the cold layers of the fluid is poor and has low thermal efficiency. Comparing the temperature profiles on the second fractions for smooth and enhanced pipes, we can see that although wall temperatures on 4 different parts are rising through the tube length, the Proust insert could reduce their temperatures with great extent. The maximum temperature reduction has been recorded as nearly 82% at x equal to 0.24 meter and on the bottom section. Here a promising fact is that after the Proust block, wall temperatures start to increase but cannot reach the previous maximum values. The reason for such behavior attributes to the fact that the novel structure of Proust media produces recirculation, breaking thermal boundary layers and leading to an improved convective heat transfer coefficient, so air could convey higher amounts of heat from the wall. A detailed investigation on the local effects of Rashek rings shows that arbitrary positioning of the rings can be important and produce some local effects on the tube wall. For example, P1, which lacks a good contact between the tube wall and the Proust media, is not able to transfer the heat through conduction, causing a low cooling effect on the tube wall. P2 highlights that not only the contact is important, but also the way two faces of wall and rings are in touch is crucial in heat transfer. For instance, when rings are perpendicular to the fluid flow direction, heat cannot be exchanged as much as the time when rings are parallel to the fluid direction like P3. So P2 and P3 sections do not have the same contributions to the cooling effects due to their different attachment. Lastly, the number of the effective rings also varies with respect to the load on the wall, where in the upper section, which has the lowest intensity of solar radiation, the heat cannot penetrate more than one ring layer. However, this number increases to 5 layers at the bottom section of the tube. This can help in optimization of such matrix in the next studies. Thermal performance in terms of 3D tube wall temperature is presented here, considering the full pipe in the second fraction for both smooth and enhanced pipes. As shown on left, the temperature difference between the two tubes at the bottom part is significant. Moreover, the Rashek ring Proust insert not only can affect the length that is covered by its dimension, but also its upstream and downstream are influenced and have been benefited from its cooling effects compared to the smooth pipe. The Sankey diagrams developed for two pipe models concerning the thermal losses show that Rashek ring insert could increase the useful heat up to 21% and reduces the thermal losses from 21.8% to only 4.2% of the total solar energy received. And finally, here are the main points found in this research. The Rashek ring Proust insert uses the higher heat transfer area as well as breaking fluid thermal boundaries to enhance useful heat while producing some pressure drops. The application of the radiation model needs attention and consideration of the fact that some rays will be sacrificed through the ray tracing at the inlet and outlet edges, so to mitigate this issue, models must be encased to block extra ray emittance. More experimental studies are needed to optimize the structure of such Proust media for the integration with solar collectors. Thank you so much for your attention.
Session A4, and we will see you tomorrow in the last day of the International Conference of Renewable Energy and Power Quality. Thanks a lot for attending this session.